This is section 3.5. Trigonometric functions, the derivatives of trig functions. So let me remind you how these functions look like. So sine of 0 is 0 at 0, and it increases to 1 at pi over 2, and it decreases back to 0, and in fact until negative 1, and it increases back to 0. So it goes up and down. Well, sorry, this is supposed to be 2 pi. Okay, so it is positive until pi, and at 3 pi over 2, it becomes negative 1. So the values change between 1 and negative 1. So this is the curve. This is the graph of y equals sine of x. So the derivative, now let's think about the derivative. So until pi over 2, we see that the graph is rising. So we expect to have the derivative in this region. We expect to have the derivative greater than 0. A positive, a increasing graph, a rising graph means the slope is increasing. Sorry, the slope is positive and the derivative is positive. So here, after pi over 2, we expect the graph, so we see the graph falls, so it is decreasing. So what do you expect for the derivative? So the derivative of the function in this interval between pi over 2 to 3 pi over 2, it is less than 0 because it is decreasing, negative. It means it has a negative slope. Okay, the tangent lines at each point is negative. And lastly, you can consider from here to here that the graph now again is on the rise. So that would mean here also the derivative is greater than 0. Okay, so if we call this function f of x, this is how we denoted it, then we want to find a formula for the derivative function. We can see from we expect from the graph it should be positive here, negative, and positive again. But what are the values? Can we come up with a formula? So we will just apply the definition of the derivative, and we will try to find a formula for the derivative of the sine function. Okay, so let's plug in to the formula. So apply the formula for derivative function. So what was that? So remember, how do we find the derivative of a function? We take the limit as h goes to 0, the difference between 2 points, and we evaluate the function at f of x plus h. We evaluate the function at f of x and take their difference. So this is going to give us the instantaneous rate of change of the function. So if we plug in sine of x, but how do we rewrite this expression? So we will have, sorry, let me first put the limit as h goes to 0 of sine of x plus h, right? Minus, we will plug in x, sine of x, divided by h, okay? Okay, so here, in fact, we will need to remember the rules, the some or difference of angles. So sine of a sum of angles. So you have seen these rules in your trig or in your pre-calculus classes. I don't think you took pre-calculus, but in trig, you must have taken trig. So you can check the textbook for the formula, but let me remind you. So we will evaluate limit h as h goes to 0, sine of x plus h. So this is sine of the first one times cosine of the second angle plus sine of the second angle times cosine of the first angle. Sine x times cosine h plus sine h times cosine x. Okay. So from this, we subtract sine of x. Okay, so we just expanded the formula for sine of sum of two functions, and we divide this by h. Okay, so let's see. We can factor out. Okay, so here we have sine x here and sine x here. So let's group them. Okay, so let's group them. So as just factor out sine of x, we find cosine of. So if we group, let me just highlight here. If we group this and this, just factor out sine of x, we will have cosine of h minus 1 over, okay, so let me just keep it, plus sine h times cosine x over h. Okay, so just the numerator, we grouped the highlighted terms and factored out sine x. Okay, so let's separate the numerator into two parts. And we will, so remember, limit of a sum is sum of two limits. So we can also separate the limit into two parts. So the first part will be sine of x times, okay, let me show you from the book. Okay, so let me come back here. So to the textbook, let me just come to page, like table of contents. If you scroll down, you will see a review of calculus. Okay, so when I click on the appendix C, you will see some useful formulas. Okay, and okay, so some fundamental identities for the trig functions, you may need to review these. And here you see the addition and subtraction formulas. Okay, so sine of the sum of two angles, x plus y, in our case it is x plus h. You just evaluate this expression, sine x cosine y plus cosine x sine y. Okay, so this is the formula. So we made use of that formula. So let me repeat what we have done so far. We had sine of x plus h, because in the function we have to plug in x plus h. And then you evaluate sine of x plus h. The red part here, what you see here, is obtained from that formula. Okay, so now look at, okay, so now what we did is here we just plugged in x plus h into sine, and we plugged in x, so just apply the derivative definition, and here we just applied the formula for the sum of two angles. Okay, so we applied the summation formula, addition formula. And now what we did was just take this and this, just group them. So here's sine x, just factor that out. So we are left with cosine h minus 1 here. Okay, cosine h minus 1. Okay, and what is left? We also have this piece left, this term, sine h times cosine x. We just copy this here. Okay, so we just rewrote our numerator. Now, so we will just split the numerator into two parts. Sine x times cosine h minus 1 over h plus, so we will just split this part and this part. Okay, so both are divided by h, so we will need to divide both by h. Okay. Okay, so normally it was like this. So we had these in the numerator, right? Both terms. So we just split the numerator into two. And what we can do is we can just write the terms with x separately, and we can write the terms with h separately. Okay, so we just split into two parts. Okay, so this is going to be the proof, and I will just show it for the sine function, and for the rest of the functions, we are not going to be going into this detail. Okay, so we are just practicing here how to obtain the derivative by applying its definition. Okay, by applying this formula. So now, so sine of x, it doesn't depend on h, so we can just take it out, and we can say sine of x times the limit as h goes to 0, cosine h minus 1 over h. Plus, here, now cosine h doesn't depend on h, so cosine x doesn't depend on h, so just say cosine x times the limit sine of h over h, okay, as h goes to 0. Okay, so we are done, almost done. So I will not go over the derivation of these limits, but I will just show you graphically. Okay, so this limit and this limit. So realize that we have h in the denominator, so division by 0 is not defined. However, this can be shown with other approaches. You can check them online, you can check the textbook. The textbook has the derivation of these limits. So this expression I will show you graphically. This limit goes to 0 and this limit goes to 1. Let's see it graphically. For example, the second one, sine of h over h as h goes to 0. So if you graph it, if you graph the function sine x over x, so I'll get close, as x goes to 0. So look at this curve. This is sine x over x. So when x equals 0, it is undefined, because at 0, the denominator is 0, so it is undefined. However, remember we talked about like discontinuities, and if we have a whole discontinuity, we can just, the limit still exists. So the limit of this expression is 1, okay? So it approaches y equals 1. So the limit, yes, so limits of this expression, sine of h over h, as h approaches 0, is 1. And if you graph cosine x minus 1 over x, so let's do that too. So cosine x minus, what was that? 1 over x. Let me just double check, I forgot. Cosine x minus 1 over x. Okay, sorry. So if you look at the second expression, we see that at 0, look, at 0 it is undefined because the denominator is 0. However, around that point, very close x values, for very close x values, the y value is 0. So we can, say that this limit is 0. Okay, so graphically we can see it. So what happens? So what cancels out? Well, sine x times 0 will cancel out. So the result, what do we end up with? the result of this limit, since this is 1, will just be 1 times cosine x, which is cosine x. Okay, so long story short, thanks for your patience, and I recommend you just go over this proof. It is not difficult, but you might need to review it to understand. So the take-home message is that the derivative of the sine function is the cosine function. So here we just wanted to find the derivative of the sine function, and we ended up with the cosine function. Okay, so this is what you should know as a rule, and let me in fact take you to the text again and look at the table of derivatives, appendix B. So if you go down, this is going to be the first thing under trig functions that you will see that the derivative d over dx of sine of x equals cosine of x. Okay, so the derivative of the sine function is cosine function, which we have just derived using the definition of the derivative. Okay, so you can do the same thing. You can go through the same steps, and I just recommend you can try it for practice for the cosine function. You want to go back to this page. So this page has all the formulas, and in fact we will just talk about formula 12 now. So I was just saying you can repeat the same steps or similar steps for practice to derive this formula. You can derive formula 12. It is very similar to what we have just done. So you can obtain the derivative of cosine function, and if you do the same calculations like similar, you will find that the derivative of the cosine function is negative sine of x. But these are two common functions, like two functions that are commonly used, and you should remember that the derivative of the sine function is the cosine function, and derivative of the cosine function is negative sine function. So let's go back to the graph of the sine function. So remember, we said that this is the graph of the sine function, and we figured that it is increasing until pi over 2. It is decreasing until 3 pi over 2, and it is increasing again until 2 pi. Let me show you on the graph. So let's look at this graph, and remember the sine is a periodic function, so the shape will repeat itself. So it's going to keep going up and down, up and down. Okay, so here we just draw this function for one period. So we said that it is increasing until pi over 2. Okay, until here, pi over 2. It is decreasing, let me mark them. And it is decreasing between pi over 2 to 3 pi over 2. Takes the value negative 1, and it is increasing again. So we found that the derivative of the sine function is the cosine function. Okay, so let me also draw this between 0 and 2 pi. So I just want to look at the sine of the cosine function. So realize that from 0 to pi over 2, the blue curve, which shows the cosine function, is above the x-axis. It is positive. So whenever it is above the x-axis, it is positive between 0 to 2 pi. Here we see that the sine function is increasing. Okay, so because it is derivative, which is the cosine function, since it is positive here, the graph, the red curve, is increasing. So from here until here, so from pi over 2 to 3 pi over 2. Okay, so let me just mark again, pi over 2 to 3 pi over 2. The red curve, which is the sine function, it is decreasing. Okay, so from pi over 2 to 3 pi over 2, the red curve is falling, it is decreasing. And this is consistent with the fact that the blue curve is negative. So here it takes negative values, right? It is negative all until here. And the red curve, it has a negative slope. So it has a negative derivative. And from here, so let me clean up again, from 3.2 until 0, sorry, until 2 pi, sorry, the red curve is increasing again, and this increase is confirmed by the positive value of its derivative. So the blue curve is above the x-axis, which means the slope, or this derivative, this function being positive, means the slope of the tangent line to the red curve is positive, so it is increasing. Okay, so here we just compared the graph of a function and the graph of its derivative. Okay, so you had similar problems for other functions. So here we just compared the function sine of x and its derivative cosine of x, and how does the derivative change. So far we are just looking whether the derivative is positive or negative, above or below 0, and how that changes the function. So again, if the function is increasing, the derivative has to be positive. If the function is decreasing, the derivative has to be a negative value. Now, let's derive the derivative, the formula for the derivative of the tangent function. Okay, so let's find the formula. However, you can do it using the definition of the derivative. We will just use trig identities. So I'll just say trigonometric identities. And derivative formulas. Okay, so using the trigonometric identities, we will rewrite the tangent as a function of sine and cosine. And since we know the derivatives of sine and cosine, we will make use of the rules that we learned for the derivatives to obtain the derivative of the tangent function. Okay, so any help? So could you help me find this? How can we rewrite tangent using sine and cosine functions? Can you rewrite tangent of x using sine and cosine? So sine of x over cosine of x, okay? So tangent is sine over cosine. Now, what rule can we use to find the derivative of a quotient? So we can make use of what rule? The derivative of a quotient, we can use the quotient rule, okay, as the name suggests. And what was the quotient rule? The derivative of the top times the bottom function minus the derivative of the bottom times the top function. Remember? Divided by the square of the denominator. Okay, so the derivative of sine. So I will just write it like this. So the derivative of the first top function times the bottom function. The derivative of sine times cosine minus derivative of cosine times the sine function, divided by the square of cosine function. Okay, so this is, we just applied here the quotient rule. And let's see what, so now let's plug in these values, I mean these expressions. So what is the derivative of sine? We had found this to be, so derivative of sine is cosine. Thanks, Raja. Cosine x times cosine x here, right? Minus derivative of cosine. What did we find for that? Derivative of cosine, we found, that's right, negative of sine times sine of x, right? So this is just in the formula, divided by cosine x squared, which could also be written as cosine squared of x. Now, so we have cos times cos, which is cosine square x, minus times minus will be plus, sine times sine, sine x times sine x will be sine squared of x. Okay, so does this remind you any identity? So what does cosine squared plus sine squared equal to? Do you remember? This has a name, Pythagorean theorem, and it's probably in the textbook. So when you check, let me go back here. When you check the review of pre-calculus, you should be finding the identities for trig functions, and the fundamental identities you will see. The first one is that the squares, sum of squares of sine and cosine equals 1. Okay, so this cosine squared plus sine squared equals 1. So we get 1 over cosine square x. And we have a special name for that. Do you remember what do we call this function? So 1 over cosine of x is the secant function. Let me just show it from here. So remember, cosine is adjacent over hypotenuse, and secant is hypotenuse over adjacent. So secant is 1 over cosine. Okay, so 1 over cosine squared will be secant squared of x. Okay, so what we found, so we found another rule that the derivative of the tangent function equals secant square of x. Okay, so we found the derivative of the tangent function by just rewriting tangent in terms of sine and cosine and applying the quotient rule for this quotient. Okay, and we just use some trig identities to simplify. And we found that the derivative of the tangent function is secant square of x. Any questions? So let me show you the textbook. We will go to the appendix where we have the table of derivatives. So we see here that the tangent function, its derivative is secant square x. So we already showed the first rule. We proved the second rule using the derivatives of sine and cosine. So I'm not going to be going over these other formulas, but you should either know these or just know where to find them. Okay, let's do some problems. Let's find the derivative of the function 5x cubed times sine of x. Okay, so the function is 5x cubed times sine of x. Let me write another function. In both questions, we would like to find the derivative of the given function. How would you find the derivative of the f function? So the function f is product of two functions. Okay, so if you just say, if you keep 5 with the x cubed function, so you can just say this is 5x cubed function times the sine function. To find the derivative of this function, what rule should we use to find the derivative? So we will use the product rule, which tells us to find the derivative of the first function, so which is 3 times 5, 15, decrease the power by 1, x squared, right? 15x squared. Derivative of the first times the second function, plus derivative of the second function, which is the derivative of sine, that is cosine of x, times the first function. So here we have the second function, here we have the derivative of the second function, and here we have the first function, its derivative, and the first function itself. Okay, so this is the product rule. Factor out 5x squared, and we will have 3 sine of x in the first group, I mean in the as the first term, and cosine, sorry, x times cosine x, the second part. I mean, it doesn't look much simplified even if you factor it. So I would say you can just leave the answer like this, okay? So you can write it in either way. We learned how to find the derivative of polynomials. We learned how to find derivatives of products or quotients. And we learned the derivatives of trig functions. So any combination of these functions, you should be able to find the derivatives. Okay, so let's look at the next question. The derivative of x over cosine x. Okay. So how do we find it? What formula should we use? Now we have x over cosine x. We will apply the quotient rule. So the derivative of the top. Let me first write it openly. Derivative of x times the denominator cosine x. Now the formula itself has a minus. Derivative of the denominator times the numerator, divided by cosine x squared, right? Divided by the square of the denominator. Okay, so this is how where the denominator appears. This is where the numerator appears. So let's plug in. What is the derivative of x? The x function, just the, remember, linear function x, its derivative is 1 times cosine x. So the yellow one, we don't take the derivative, right? Multiply with the second function. Minus, what is the derivative of cosine? Negative sine of x, thank you, times x, divided by cosine x squared. Okay, so let's simplify. So we have cosine of x. Negative times negative will be positive. X times sine of x over cosine squared x. Okay, so again, this, I don't think this will simplify further. Yes, I put the x in front because if you write sine x times x, it's a little confusing. Is it sine x squared, right? So it may get you may confused. So it is better to put x in front so that it doesn't confuse, right? Find the equation of a line that is tangent to the graph of cotangent of x. Y equals cotangent of x at x equals pi over 4. Okay, so I want to check out the graph of cotangent function. So this is the graph of the cotangent function. between 0 to pi. And let's mark the points pi over 4. So cotangent of pi over 4 is 1. So if you just plot the point pi over 4, comma, cotangent pi over 4, just marks this point. Okay, so let's come back to the question. So we would like to, we need to find the equation of a line, which is going to be tangent to the graph of this cotangent function when x equals pi over 4. Okay, so you already solved the graph. Let me just copy it here. So the graph of the cotangent function goes like this. Okay, at x equals 0, at x equals pi, it has a vertical asymptote. You can evaluate cotangent of pi over 4, and you can see it's equal to 1. So we would like to, let's say it is somewhere here, at pi over 4, the function value is 1. And what are we trying to do? We would like to draw a tangent line. Okay, we would like to draw a line which is tangent to the red curve at this point. So it's going to touch the red graph at this point. Okay, so we will find the equation. We would like to write the equation for the red line, right? The red line. What do we need to write an equation? So we need a point, and we need to know the slope of that line. Then we will be able to write its equation. What is a point on this? What are the coordinates of a point on this red line? So where does this line passes through? So it is given in the question. It passes through x equals pi over 4, comma, the y coordinate here is 1. Okay, because the curve, the red curve, and the line will touch at that point. When x equals pi over 4, the y value here will be 1. So this point is on the graph of this line. How about the slope of this line? How do we find the slope of this line? Derivative is equal to the slope of the tangent line, right? So the slope of the tangent line is the derivative of the function at this point. So the function, the cotangent function, let's find its derivative. Okay, and we will evaluate it at x equals pi over 4. And that's going to give us the slope of the tangent line. Okay, so I will check the textbook for the derivative of the cotangent function, which is negative cosecant square. Okay, so this is negative cosecant square x. Okay, the derivative of the cotangent function. So the slope of this line will be this function evaluated at pi over 4. The formula of the cotangent derivative is negative cosecant square. So evaluate the function cosecant at pi over 4, find its derivative, and negate to find the slope of the red line. Okay, so we can get help from our calculators. Okay, so if you evaluate the negative cosecant squared at pi over 4, you should be finding negative 2. So we will plug in negative 2 for m, and we will be able to find a nice equation. Okay, if you rewrite it, so just multiply this. Let me just write final equation, negative 2x plus pi over 2 plus 1. So this will be the slope, -2. This will be the y-intercept. Okay, pi plus 2 over 2. And let's write it now in the graphing calculator. So you see the green line is now tangent to the red line. So they both pass through pi over 4. And the two, like the graph and the line, they just touch at that point. So this is the tangent line at pi over 4. And we found the equation of this line. Okay, so just come back here. So this is how we found. So just use that point and find the derivative of that function at that x value to find the slope of the line. So here, let me just show here. So this is the equation we got, right? So we just plug this into this formula. If you multiply -2x and you multiply by pi over 4, so this is going to give you 2 pi over 4, which is pi over 2, right? Now you multiply -2 by -2 pi over 4, so this one. And then you have plus 1 here, which is this. Okay, so -2x plus, if you get common denominators, pi plus 2 over 2. So now your equation is in slope intercept form. An example of a combination of several trig functions and polynomial functions. We want to find the derivative of this expression. And remember, we have first sum of two functions, so we can use the the addition rule. So the derivative of sum of two functions will be the sum of the derivatives. So we should check the derivative of the cosecant function. Let's find it from here. So the derivative of the cosecant function is negative cosecant times cotangent. So negative cosecant times cotangent of x. Let's double check. So the cosecant function, the derivative is like number 14, rule number 14, negative cosecant times cotangent, okay, of x. So we just find the derivative of each and we will add them. How about the derivative of this one? So we have a product here, right? X times tangent x. So we will need to use the product rule, right? Okay. So be careful. Now we will find the derivative of this term, which is the derivative of the first. So let me just put it here, derivative of x times the second function, derivative of the first times second, plus derivative of the second times first function, okay? And so this is the derivative of this product, which will be the derivative of this thing, which will be added to the derivative of cosecant x, okay? So the first one will just stay. There is no derivative here. We already found the derivative. Plus derivative of x is 1 times tangent of x. Plus, now let's check the derivative of tangent. We had found this together, which is secant square of x, rule 10. Okay, so the derivative of tangent is secant squared x times x. Again, I will just write this x, move it to the front. Let's see, negative cosecant x times cotangent x plus tangent x plus x times secant squared x. I don't think this will simplify further, so we can just leave it like this. So higher order derivatives, this is going to be the last thing we will discuss. So in fact, I would just not say example, but consider the sine function. If you take its derivative, we found that it is cosine of x. And if you want to find the second derivative of sine, how can you do that? The second derivative of sine means take the derivative of the derivative. So take the derivative of cosine. So what is the derivative of cosine? It is negative sine of x. Okay, maybe I can just show it like this. So the second derivative of sine is equal to the derivative of cosine, which is negative sine of x. And if you keep taking derivatives, what happens? This is what we want to see. If you want to find the third derivative of sine of x, so this is the first derivative, this is the second derivative, so we just keep finding derivatives. What would be the third derivative? Just take the second derivative and take the derivative again. So this negative sine x function, find its derivative. And what's that going to be? So negative cosine of x, right? Because derivative of sine is cosine. Okay, so let's do one more. If you find, we usually just denote the fourth derivative with like Roman numbers. So this will be the derivative of the third derivative, right? So we just found that the third derivative was negative cosine, and if you take the derivative of this expression again, what do you find? Negative of negative sine x, right? Because the cosine derivative is negative sine, which is going to simplify to sine of x. So what happened is, in fact, we started with the sine function, and when we took its derivative 4 times, we ended with the function itself. Okay, so in fact, if you want to find the fifth derivative of the sine function, well, better notation, let me just use that one. D over dx to the fifth derivative. Okay, so this is how we can, let me just come back to here, show the larger, like the higher derivatives, and you will be coming. Okay, so here's the book asks us to find the 74th derivative, but I mean you just to find the remainder when you divide by 4. So then you can find whichever derivative you like. So the fifth derivative will come back will be equal to the first derivative, which is going to be cosine x. So the sixth derivative of sine of x will be the next one. Sorry, this is the sixth, which is negative sine of x. So let me just write here the first derivative, or let me just okay. So the first derivative, the fifth derivative, add 4, ninth derivative, and so on. Okay, so all these derivatives will be equal to cosine x. So here we see the second derivative, the add 4, sixth derivative, 10th derivative, and so on. So all these derivatives will be equal to negative sine of x. Okay, and so on. So when you can find, let's say, if you want to find, I mean, I don't think we need to, you need to find the like 50th derivative, but just knowing that the first 10 derivatives would be sufficient, and you can just evaluate it by counting. So it's going to be the same functions will be repeated. Okay, so we will stop here.